Welcome back. This session is about comparing the average impacts of large groups of outputs with webometric, altmetric or citation indicators. This is particularly for Mendeley readers, web citations, Google Book citations and citation counts. This is quite a technical session, but it's important if you're going to be comparing average impacts of large groups of outputs to use the right kind of indicator, an effective indicator. Taking simple averages is going to give misleading results in many cases, so we need a proper indicator. The problem that we're going to deal with is, given a large group of outputs, how does their impact on average compare to other similar groups or the world average? We're going to look at both problems. For example, does Department A have more Mendeley readers per article than Department B? Or does Funder C fund research that is more downloaded than the world average? Both of these questions shouldn't be answered by taking simple averages, but must use a proper indicator. Average impact scores don't work. Simple averages don't work because of multiple reasons. The first reason is field differences. If you average across multiple fields, then this gives an unfair advantage to groups that publish in high impact fields. For example, economics has higher citations than history. So it wouldn't be fair to compare groups that publish different balances of economics and history. And time differences also affect indicators. So in general, groups that publish more of the older research will tend to get higher scores than groups that publish more of the younger research. So it's not fair to compare averages taken over outputs from multiple years. The older the research, the higher the score it gets on average, other factors being equal. Here's an example to illustrate this problem. So we have two research fields that are being compared, infectious diseases and medical ethics, and we have two groups, Group A and Group B, and both Group A and Group B publish some infectious diseases research and some medical ethics research. And here we have data on the world publication of infectious diseases and medical ethics research and the outputs of Group A and Group B. And if you look at the number of Mendeley readers per article, you'll see that Group A and Group B are exactly world average in terms of the number of Mendeley readers per article, 40 for infectious diseases and 10 for medical ethics. So they're both exactly world average. But if we take the overall average number of readers per article, for Group A it's 20, the final column, and for Group B it's 30. So the Group B score is 50% higher than the Group A score, despite the fact that both Group A and Group B are exactly average in their fields. And why is this the case? It's because Group A publishes 100 articles in infectious diseases, the high impact specialism, but double 200 in medical ethics, the low impact specialism. So because it publishes more of the lower impact specialism articles, it has a lower average reader count, 20. Whereas Group B publishes twice as many in the higher impact specialism, which is why it can have a higher average Mendeley reader count, 30. So this is an unfair comparison. Taking a simple average number of readers per article is unfair on Group A because Group B publishes a higher share of its articles in the higher specialism field. So Group B has an unfair advantage. We're going to introduce an indicator that doesn't let B have an unfair advantage. The same occurs if you have groups that publish in a single field, infectious diseases in this example, but in different years. And here both Group A and Group B publish only in infectious diseases, and they both publish articles from 2014 and 2015. But this time Group A publishes twice as many of the younger articles, 2015 articles, and Group B publishes twice as many of the older articles, 2014, and because of that, Group B has an advantage because its older articles have higher average scores, even though the Group A articles are exactly world average and the Group B articles are exactly world average for both years. So these scores show that Group B has an unfair advantage for publishing a higher share of the older articles. So we can't use an indicator such as simple averages that give an unfair advantage to any group. One solution to this problem is to calculate lots of separate scores and only compare averages between articles from exactly the same field and year. So in this case, if you want to compare Group A and Group B and they publish in history and economics, then we would make separate comparisons for 2015 and 2014 and also separate for economics and history. So we'd make lots of individual separate calculations rather than one overall average. So this works at eliminating bias, but it becomes complicated if there are many fields or years. So you might end up with the information that Group A has a higher score than Group B in 6 out of 20 contexts, but then even that doesn't mean that Group B is better, because maybe the contexts in which it has a higher score are bigger fields, and maybe the gap is smaller in the fields where it has a higher score. So it doesn't give you a straightforward answer if you make separate calculations. It's fair, but the answer isn't straightforward. Here's an example of the separate calculations. Again, we have Group A, Group B in the world. We have 2 fields, infectious diseases and medical ethics, and we have 2 publication years, 2014 and 2015. And now we're calculating separately, so we're not calculating overall averages. And we can see that for the first data row, Group B has a higher score than Group A. For the second one, it has a lower score. For the third one, it has a lower score. And the fourth one, it has a lower score. So Group A has a higher score on one of the 4. So they're not average. But it's hard to tell which is better overall, because you need to take into account the number of articles in each group and the size of the difference. For example, Group A is better than Group B, has a higher score than Group B for the Medical Ethics 2015, the bottom row, but the difference isn't big. It's 4 compared to a difference of 20 in the top row. On the other hand, the average scores are much lower in the bottom row than the top row, so does it make a difference? So it's difficult to tell. It's not straightforward to make a decision based on this data about which is the best performing group, assuming that you need to make that decision, or at least the group that produces the highest scores overall. In this example, we could make a decision. We could see that Group A and Group B are both average and they're both equal in each group, so there's no problem. So we can see that they're the same. But this is the exception. Most of the time, some groups you could expect to have higher scores than other groups in some fields and years, and the opposite way around in other fields and years, giving a complicated situation. And this is only an example for 2 fields and 2 years, and is quite likely to be the case that a large group would publish in 10 or 20 fields, and maybe the evaluation covers 5 years, in which case you could easily have 100 sets of numbers to compare. One solution to this, the standard solution to this, is the mean normalized citation score, MNCS. This is from Leiden. And for this gives a field, a normalized indicator, where you divide each score by the world field and year average, and then you average the normalized scores. So you normalize citation counts by dividing by the average for the world for that field and year, and then you average the normalised scores rather than the original scores. So this gives what's known as the MNCS. Let's see how that works. So MNCS values are unbiased and fair to compare between groups, even if they publish in different specialisms and years. And the MNCS value is always 1 for any field or year. And scores above 1 indicate impact above the world average, and below 1 indicate impact below the world average. So let's have a look at the worked example of this. So this table shows 6 articles with an MNCS score of 1.5. Where does the 1.5 come from? Well, for each of the 6 articles, the number of citations is recorded in the second column, and in the 5th column is recorded the world field and year average citations corresponding to that field and year. So the average number of citations per paper for the whole world for infectious diseases in 2015 is 3. For 2014 it's 5. For medical ethics in 2015 it's 1, and for 2014 is 2. So we divide column 2 by column 5 to give the normalised citations. It's the citations divided by the average for the field and year in which the paper was published. So if you look at the third row, 10, and the article got 10 citations, and on average papers in its field and year got 5 citations, so its normalised citation count is 10 divided by 5, which is 2. So if we normalise all the articles in this way and then we average them, we get 1.5. So on average his articles are cited 1.5 times as often as normal for the fields and years in which it was published, or its impact is 50% higher than the world average for these 6 articles on average. So if you like to do a little bit of maths for practice, can you calculate the MNCS scores for this group, please? So pause the presentation now, work out your answers, and then continue, and I'll show you my answers. So here are my normalised scores, and I get 1.25 overall. So this group has an MNCS value of 1.25. Its articles are cited 1.25 times as often as normal for the fields and years in which it published. Its work has an impact 25% higher than the world average, in other words, and this is mainly due to Article 7, which has a very high normalised score. It's expected to get 2 citations, but it got 10 citations, so 5 times higher than expected. The MNCS has limitations, which I'm just going to go through. One statistical limitation is that indicator data is highly skewed. That means there are many low values and few very high values. And if you take the average of a set of numbers that includes very skewed distribution, then it doesn't give you a very good estimate of the middle of the data, because it's too sensitive to the presence of very high value. Individual very high values can make a big difference to the average. And the confidence intervals, if you try to calculate them for the data, they'd be wider than necessary. And this skewed pattern is true both for the raw citation counts or altmetrics and also for the field year normalised data. So the field year normalisation doesn't get rid of the skewing. And we can see the skewing issue in the previous slide, where the one Article 7, if we take that article away, the MNCS changes from being 1.25 to 0.71, substantially above the world average to substantially below the world average of 1. So this is a limitation of the MNCS. And here's an example of highly skewed data. These are the Mendeley readers and the Scopus citations of a set of orthodontics articles from 2009. And you can see very high numbers of articles with no readers or no citations, and small numbers of articles with over 60 readers or over 60 citations. So this is what it means to be highly skewed data. Lots of very low numbers and small numbers of very high numbers. So the solution we're going to adopt to this skewing problem is to log transform all the indicator values, the citation counts or the altmetrics, to reduce or eliminate skewing. In most cases, it essentially eliminates the skewing. And to do this, we add 1 to the indicator score, and then we take the natural log, ln of 1 plus x. And the spreadsheet here shows how you can do this in Excel. Why do we add 1? It's because many scores are 0 and the natural log of 0 is undefined. So adding 1 gets around this problem. It's a standard method of getting around the problem that you have to take a log of a data set including zeros. And we calculate the average log 1 plus x score for each field in year separately. So when we divide by the average, it's the average not of the citation counts or the altmetric scores, it's the average of the log 1 plus citation counts or the average of the log 1 plus citation scores. If we log transform Mendeley readers or Scopus citations, we get a much less skewed data set. If you look at these two graphs, you can see they still look skewed, but now there are big gaps either side of the bars, indicating that on average the skewing is substantially less. Here are some calculations for the separate calculation example. If we were going to calculate the log transform scores separately, this wouldn't be useful, but this is just to illustrate the procedure. Then we would, for each group, we would calculate the average of the log 1 plus readers or log 1 plus citations per article. So we'd start by taking log 1 plus readers, and then we would average all the results, or log 1 plus citations, and then average all the results. And if we want to calculate confidence intervals for the log normalized data, then for a set of n outputs with the web indicator values C1 up to Cn, the log transformed values would be log 1 plus Ci, let's call it Ci dashed. Then for the arithmetic mean of the log transformed values, the 95% confidence interval could be given by the standard normal distribution formula, the average plus or minus 1.96 times the standard deviation over the root of n, if the skewing is sufficiently reduced. So we can have a simple confidence interval, and that's not true if you don't do the log normalization first. You can't get a formula for the confidence interval. You could only generate a confidence interval by some kind of bootstrapping method. So we're going to use the mean normalized log transform citation score variant of MNCS, which includes the log transformation as follows. So the MNLCS is identical to MNCS, but has one additional step. We log transform all the data before we do any calculations, before we do any averages. So we add 1 to all the citations or altmetric scores, and then we take the natural log. MLCS will then be less affected by individual values than the MNCS, and we'll be able to calculate a confidence interval for it. And as for the MNCS, the MNLCS is always 1 for any field, and a score above 1 indicates impact above the world average, below 1 indicates impact below the world average. So what is the definition of the MNLCS? So for a set of n articles with citation counts or web indicator values C1 up to Cn, we let Li be the arithmetic mean of the log transformed counts for the world's papers from the same field as year as Ci. Then the MNLCS would be the normalized log transformed citation scores for each paper. So the log transformed citation score divided by the world average log transformed citation score for the appropriate field in year. And then we average all these log transformed values. So it's the same as the MNCS score, but with the extra log transformation step. And here's an example, a worked example for the MNLCS. Here we have 6 papers, same 6 papers as in our first example, from 2 fields, infectious diseases and medical ethics, and 2 years, 2014 and 2015. Now the extra step we need to put in is we need to log transform the citation counts. So we start with start with the second column, and we log transform it to get the 6th column. So the 0 will be log transformed to log 1 plus 0, which is still 0. 3 would be log transformed to natural log of 1 plus 3, natural log of 4, which is 1.39, and the same for all of them. And then we divide the log transformed values by the field year average of the log transformed values. And then we average them all. So here we have 6 normalized citations that total to 6.99. We divide them by 6 and we get an average of 1.16, which is the MNLCS value. So after the log transformation, this group's articles are cited 1.16 times as often as normal for the fields and years in which it published, where its impact is 16% higher than the world average on the log transform scale. So if you'd like to do an exercise, then can you try this out with this set of 8 articles, please? Pause the presentation now and restart when you're ready to continue. Here are the results. So you should find that the score is to 2 decimal places 1.00. So this group has on average exactly world average citation impact for its papers. If we look at again at high impact articles, if we take out the high impact article 7, then the MNLCS still falls quite a lot, from 1 to 0.64, but it's smaller than the fall for the MNCS. So the MNLCS has reduced the impact of the individual article. And confidence intervals, as I've mentioned before, normally we can't calculate confidence intervals with a formula. We'd have to use bootstrapping to calculate them. But for the log transformed indicators, we can use a normal distribution formula. And if you use Web Metric Analyst, then confidence intervals are produced for the MNLCS scores using an appropriate method, Feeler's method, for the ratios of normal distributions for this calculation. So you don't need to calculate the confidence intervals yourself. They're automatically included in the Web Metric Analyst output. And for large fields, this is equivalent to the student's t-distribution formula that was shown on a previous slide, plus or minus 1.96 times the square root of n over, sorry, s over the square root of n, plus or minus 1.96 times s over the square root of n. Sampling issues. A practical problem is that for the MNLCS calculations, you do need the indicator scores for all the world's articles in each field or year covered. So to world normalize, you need the world's data. Unfortunately, this is a lot of extra data that needs to be collected. It's not needed if you're comparing groups to each other separately for each field year combination, but it is necessary if you're doing a combined comparison of 2 groups together. You can't avoid getting the world data for that. But if large-scale data collection is a problem, then you might be able to get away with a random sample of the world's articles instead of 100% of the world's articles. In the workshop, we look at ways to do this. It reduces the accuracy of the results. You get wider confidence intervals, but it still may be a practical solution. And webmetric analysts can help with the random samples, as we'll see when we go into the practical session. To summarize, we're going to calculate an indicator that will compare the impacted groups with publications on any indicator, citations or altmetric, first log transforming them with the log 1 plus x formula. This is done for you by webmetric analysts, so you don't have to do the maths yourself if you don't want to. And then we compare the average indicator separately for each field in year biases. This is the separate calculations strategy, or compare MNLCS values between groups or against the world average of 1. And this is the recommended strategy if you can get the world data or the random sample of world data. And we can use confidence intervals to assess the statistical significance of any differences. And these methods work best for indicators with high scores, which include Mendeley readers, web citations, Google Book citations, downloads, views and citation counts. They don't work well for the webmetric indicators such as syllabus mentions, where most of the scores are 0. So we'll look at another method to deal with that issue. So thank you very much for listening, and we'll look at another method at the next presentation.